Hello, everybody. So I'm part of Hexagon Cradle Solutions. So first of all, let's talk about a few words regarding who is Cradle. So Cradle is a Japanese company founded many years ago in 1984, and as you can see, we have a lot of great customers because our footprint is around 90% of the top 10 major OEM. We were recently acquired by MSC, and then we are part of the Hexagon family. So the good point regarding the Cradle spirit is the katana. So this means that we are fast, accurate, robust, easy of use, and also the multi-physics focus. So why you should consider Cradle? So as I said, as our spirit is about the katana, so a pragmatic tool that can be used by a customer. So that's why we have some kind of good user-friendly interface just to handle efficiently any kind of simulations. And this is not about user-friendly, but also to consider complex, let's say, real geometry. So that's why we made a lot of focus in meshings. So we can handle, let's say, 30,000 parts, and we can mesh it really quickly. And in combination to the solver capability in terms of accuracy and speed, we can combine also the complex things such as motion using offset techniques, mixed phase up to DEM, and they will take and show you some example in terms of multi-phase capability in combination to thermal, and especially for the thermal, when we talk about a lot of parts, for sure we need to get a robust and fast meshing for that. And because of all these things on multi-physics capability, including co-simulations, that's why we are trying to collaborate with our customers. So that's why we have this very high satisfaction rate, 95%. So that's why we are proud of this number. So regarding the CFD, for me, the CFD is everywhere, and I discover new area every time. So that's why we have different application areas. So for sure in aerospace and defense, when we talk about turbo machinery, transonic, supersonic, or even subsonic, we are developing also some hypersonic capability, which will come very soon. Chemical process, marine and oil and gas, especially the efficiency of in the marine. It can be on the propeller, taking into account the flow around the hulls, considering the propeller motions, the cavitation, erosion. So this can be a really complex physics. Even in a maybe simple way, but not so easy, can be consumer goods, considering, let's say, closes using DEM simulation, the rotation of system, and even free surface analysis. Electronics, a lot of applications, considering you very large assembly of different parts, and we have some dedicated tools to extract. Okay, not only it's red hot, it's let's say hot or cold, but why we got this result. And in terms of design, to extract the right information is always important. So I can talk a lot more, but let's move on some specific areas. If we take the example of the energy, let's say in terms of extreme weather conditions, especially for floating structure, we need to consider especially the wind loading on structure. This one can generate waves, and in addition some resonance effects. So we'll discuss a little bit more on the crane applications. We can discuss about the green technology efficiency, let's say on the wind turbines, or considering different effects, especially the thermal side, solar radiations, or thermal radiation in additions, or even, let's say, storage and process design, or even transport efficiency through piping, or even granular flow using ODM, and maybe more, such as the drilling efficiency through the system. So let's have a deeper look on some real example.
You're halfway through.
Yeah, perfect. So let's take a deeper look on the drilling bit application, crane, and rocket exhaust analysis. So for the drillings, so as you can see on the picture, and maybe some of you know perfectly this part, even the motion of the drilling part, as you can see on the videos, can be really complicated to extract, and especially because it involves very high non-linearity inside. But on the CFD side, instead of only the structure, we can be involved in such simulations, such as to estimate the drag force acting on the drilling bit, to handle the complex motions, or even the particle generation due to the motion of the system. So really complex. And for that, we were able to define the difference, the combination of translation and rotation at the same time, including the fluid inside, which is for sure non-Newtonian flow using the Karo-Yasuda law, where we include also the discrete element method with cohesion process just to create this effect. Regarding if we move on the crane under wind loading, so for sure, as you may understand, most of the crane would like to support some specific things, such as, for example, the very high load system. But the wind loading, and especially for extreme weather conditions, could be generate for sure a very high load due to the pressure force acting on the structure. But also, it can adjust the crane position depending on the wind, and maybe generate some resonance due to the vortex shading. So as an example, let's have a look on the two simple samples. Let's say if you are tracks that move on and sudden wind across wind, you can see that directly the effect of the pressure across the track motions. And because of the vortex shading, or even let's say pressure fluctuation acting on the wings, this need to be taken into account on the system. And for both of these, we need to exchange information between the CFD solver and again the structural side, or even the multi-body dynamics. So that's why we have SFlow to Nastran to smoothly exchange information from this fluid session to the structural session, or even co-simulations, two-way coupling to exchange at each time step the effect. And as a result, you can see a simple picture of the same crane. Let's say you see the pressure force acting on it and the vortices generated behind. And as a result, we exchange the information just to extract the structural deformation and the stress acting on it. And another interesting application can be the rocket exhaust analysis.
2 minutes.
Yeah, perfect. So especially when we talk about high compressible fluids, we need to handle different specific points. One is to be able numerically to get a stable calculation. So that's why you have different Riemann solver, as you can see, that can adjust the stability and the accuracy depending on your simulation. But we have the default one is typically an automatic way between adding stability where it is needed, regarding the precision when it is needed. And because this is not sufficient, we also add some acceleration, because without any compromise on the accuracy. So that's why you see activating some Jacobian free and Newton trade-off acceleration, we are able to speed up in average by 2 times faster. And because shock waves are not easy to capture, we can link this density-based capability with mesh adaptation to capture accurately the flow structure and the shock waves that can be in interaction, such as, for example, the boundary layer. And as an example, if I take this rocket analysis with, let's say, certain amount of pressure on the inlet, and we use, for example, 3-step adaptation, which where the last mesh is 0.5 million elements, and only two hours is necessary to compute all these system and to capture the shockwave, as you can see on these pictures. So this is the end of my presentation. So if you have any questions, do not hesitate to put it in there.